Recently, I built a 8-bit ALU from scratch and named it SCESNA 1, a computer that shows how computer works. And the best part is it comes with its own compiler, SCESNA/C++. So today I am going to share all my thoughts while creating it and also explaining it from low level to high level. So ALU consists of these 5 fundamental things: adder, subtractor, OR, XOR, AND. So I added only 2 things, adder and subtractor, because I am making it for a school purpose. So most people out there don't understand logical operations like NOT, AND, XOR, or very beginning, these two switches define the opcode, deciding which operation the ALU performs. For example, this ALU uses 00 for addition and 01 for subtraction. Spoiler alert, while the physical build did not work out, the entire system runs in a digital simulation. The physical build failed because the ICs were damaged by an incorrect 9-volt power supply. That was a painful mistake but also a valuable one. So instead of stopping, I rebuilt the whole design in simulation, where every bit, every signal is visible. This actually unlocks something better. Because the CPU has no clock, it's purely combinational. The moment you change an input or opcode, the output updates immediately, even without physical hardware. This is still a ALU built from real logic following the real rules, and this is the exact foundation where every modern CPU is built on. Alright, before doing anything fancy, let's do a basic test run. Let's ask a simple question. What is 5 plus 9? First, I set the opcode. Since this is an addition, the opcode is 00. That tells the ALU perform add. Now I set the first operand. 5 in decimal is 101 in binary. So I flip these 8 switches to represent 5. Next, the second operand. 9 in decimal is 1001 in binary, again 8 switches. At this point, nothing is being executed step by step. This ALU is combinational. The moment the inputs are correct, the output appears automatically, and the output we get is 110. That's 14 in decimal. So 5 plus 9 is equal to 14, what we expect. This tells us 2 things. Once a simple test like this passes, we can trust the ALU for more complex operations. Its job is to take a human-readable instruction and translate it into exactly the bit pattern the ALU understands. For example, when I write add 5, 9, SCESNA converts that into an opcode. Operand 1 in 8-bit binary, operand 2 in 8-bit binary. These bits map directly to the switches and input on the ALU. No abstraction. This means the compiler and the hardware are designed together. If I change the ALU, SCESNA has to change too. That tight coupling is intentional. It's how early computers were built, and it's the best way to truly understand what a machine is doing. So SCESNA is basically the translator between software ideas and raw logic gates. And once this layer is solid, everything above it becomes possible. So that's the system, a working ALU, a real test run, and a compiler that speaks its language. Even though the physical build failed, the ideas did not. The logic works, the translation works, the understanding is real. This project is not about being perfect. It's about going low level enough that nothing is hidden. GitHub link is in the description. Thanks for watching.